So what we looked at last time was graphing. And the idea of graphing was that we have this XY plane. And we came up with this way of plotting points. Now this plane, it's two number lines that cross each other. So if we want to plot the point 2, 1, now what that means, this is called an ordered pair. So when we plot 2, 1, the first number is what we call the x-coordinate. The second number is the y-coordinate. So what this means, we put a vertical line at x equals 2, and then a horizontal line at y equals 1. And we draw these lines long enough so they intersect. And when they intersect, that's the location of our point on the Cartesian plane. So that's 2, 1. Now, the other thing we looked at were functions. And we did a function last time called x squared, or x to the power of 2. And so we had f of x is equal to x squared. So if we want to find a value of this function, we have to give it an input. So we'd put an input for x, and then we would ultimately get an output. So we could take f of 2, that's going to be 2 squared. In other words, we replace x with 2 everywhere we see x. And that will give us 4. So what happened is we took 2, we put it into the function, the output was 4. And so what we would do is we would make a chart of inputs paired up with their outputs. So for input, we have our output. And oftentimes, we'll call f of x y. And then we can graph these. We have a vertical line at 2, horizontal line at 4. And that's how we would graph this one point for this one function. So questions about that? All right. So continuing on, we'll do another graph of the function. And then I'll show you some generic graphs or graphs of what we call canonical functions. And these you're going to be doing things with later on. You'll be moving them around, translating them, and so forth. First off, the input, x, We have a special name for this. We call it the independent variable. Now, the reason we say x is independent is we're usually free to choose x. We could let x be 4, we can choose x to be -10, and it really doesn't matter. Now, there are sometimes restrictions on what x's we can choose. This is a concept called domain. For example, if we're dealing with the square root function, we'll get to look at that today, we can only choose numbers that are positive or 0. And the reason is we can't take square roots of negative numbers, at least not yet. That is something that can be done, but not if we're looking for real number outputs. Again, a real number is integers, things you count on your fingers. Fractions are real numbers. Square root of 2 is a very complicated real number. It's an irrational real number. When you take square roots of negative numbers, you're getting what's called complex numbers, and that's a whole other conversation. So sometimes you do have limits on the x's you can choose, but a lot of the time you don't. So output y. Well, the output y, we call this the dependent variable. The reason we call it the dependent variable is because it's dependent upon the value you choose for x. So we sort of have to wait to find out what y is going to be. You choose x, do the calculations, and then we'll discover what y turns out to be. It depends on your choice of x. Now let's take a look. Let's let y, or f of x, y and f of x are interchangeable. Let y be the absolute value of x, or put another way, the distance x is from 0. In fact, let me write this a little differently. I'm going to do it horizontally, just so we have more room. So I'm going to choose these as x's. Now, if you recall, the way we figure out the distance between a number and 0 is we just make it positive. So the absolute value of -2, just going to be 2. Absolute value of -1 will just be 1. Absolute value of 0 is 0. Absolute value of 1 is 1. Absolute value of 2 is 2. So now we're going to graph this. Now I've graphed this function a bunch of times, so I sort of know how it looks like. So that's why I know we're only going to need the top half of the Cartesian plane. Now, as you get more experience with this, you'll figure that out as well. But if you're not familiar, don't worry. Graph as much of the plane as you think you'll need, and then you'll see where your graph ends up. Now, first off, if x is -2, y is 2. So we would put a vertical line here. We'd have a horizontal line here, and they're going to intersect, looks like right about there. Now, there's different ways of locating these points. What we did last time is you'd put a vertical line here, and then a horizontal line here, and we put a point where they intersected. Another way you could think of, though, is you can take a walk starting at the origin, come out to -2, and then we got to go up or down to the y. Well, the y is going to be up here. So you can walk out to here, then walk up to here, and that's going to be your point. But however you want to locate the point, you can use the vertical and horizontal lines as well. Whatever method's going to work. So for -1 and 1, I'll walk out to -1 and then go up to 1. 0 and 0. Well, I start at 0. Okay, so I just stay here. And then I go up to 0. But 0 is also vertically located here. This is what we call the origin. 1 and 1. I walk out to 1, and then I go up to 1. Now, if it was -1, I go out to 1, and drop down to -1. And then for 2 and 2, I walk out to 2. And in this case, I go up to 2. And then I connect my points from the left point to the rightmost point. So here to here to here, here to here. And this would be y equals the absolute value of x. Questions about that? So let me show you some, as they say, canonical functions. So one kind of canonical function. Y equals x. And it's this line. Comes out at a 45-degree angle, 45 degrees to the x-axis. Now this one we saw yesterday. Now the version we drew yesterday, it was more jagged. If you use finer points, instead of -1, I'm sorry, instead of -2, -1, 0, 1, and 2, if you use -2, -1.5, -1, -0.5, 0, 0.5, 1, 1.5, 2, and then cut up the inputs even more. What you're going to get is something that doesn't look jagged. It actually smooths out like that. So that's y equals x squared. Y equals x cubed. The one we just saw. Let's see, do we have some other ones in here? Y equals square root of x. And then y is the cube root of x. We might not have ran into this one before. But these are typically our canonical functions. And what I mean by canonical is we'll do some graphs, and we'll take one of these sort of basic graphs. So they're going to be, we'll treat them as they're basic. Doesn't mean they're easy. And then we'll modify them in some way. We'll add things to them. We'll multiply things to them. We'll move them around. So any questions about that? All right. So I'm going to move on to section 1.4. And with this, we're solving linear equations. So again, this is kind of a review. So I'm going to sort of just shoot through different examples of these. And we're going to talk about some situations where we don't always get the solutions we expect. So first off, let's say we have this. What we want to do is we want to undo PEMDAS. So if we think about what PEMDAS is, we have 5 times x plus 3. So we want to go backwards. Now in PEMDAS, multiplication is before addition. So if we knew what x was, we would go 5 times that number, and then we would add 3. To undo that, we're going to do the opposite of adding 3, and then the opposite of multiplying by 5. So what we have, opposite of plus 3, is minus 3. So we're going to subtract 3. We want these numbers to disappear, but we got to be careful. This symbol here is the equal sign, and that says everything has to be balanced. So if we take away 3 here, we also have to take away 3 on the other side. So what we do to one side, we have to do to the other side. So if we subtract 3, cancel it, we've got to subtract 3 over here. And again, what we're doing is we're thinking PIMDOS backwards. So this would usually, if we knew what x was, we would do this first, and then we would do this. Doing PIMDOS backwards, we'll undo this, and then undo that. So under PIMDOS, we do 5 times x, and then we would add 3. If we're going to reverse everything, we'll subtract 3, and then we'll divide by 5. So if we're going to multiply, if you follow PIMDOS, this would come first, and then you would do this. But if we're going to do the opposites, we have to also reverse PIMDOS. So we'll do the opposite of -3, and then the opposite, so we'll do the opposite of adding 3, which is minus. The opposite of multiplying 5 is divide. So we do everything backwards. So I should mention real quick before I jump into this, what are the opposites of operators? So for opposites, addition and subtraction are opposites. And then multiplication and division, they are also opposites. So what we'll do for an example, 5 times x plus 3 is equal to 18. We're going to go backwards through PIMDOS. So instead of dealing with this and then this, we'll deal with this and then this. And we're going to deal with them by doing the opposites. So we'll subtract 3 from both sides. These will cancel. And we'll get 5x is 15. And now we'll do the opposite of multiplication, which is division. So that'll make these cancel. And what we'll get is x equals 3. And that's going to be our answer. Now, questions about that? I'm going to do another example. Let's say we have this. Well, in this one, what we want to do is gather like terms. So to gather like terms, we want all the x's moved to one side, all the numbers moved to the other. So all the x terms on one side and the number terms on the other. Now, there's different ways you can do this. I'll do it both ways. There's generally two ways. We're going to want x terms on one side and numbers on the other. You'll hear people talk about this as moving something to the other side. It's a very common way of describing it. So we can use that also. So what I'm going to do first is I'm going to move x to this other side. And the way I do that, if I have a positive x, I want x to disappear. So if I subtract x from x, it goes away. But what I do to one side, I've got to do to the other. So my x's cancel out on that side. X minus x is 0, just like 3 minus 3 is 0. And so I'm going to get 7x plus 1 equals 43. Now, if I subtract x from x, what I actually get is 0. But 0 plus 43, well, that's just 43. That doesn't change anything. So that's why I'm skipping a step is what I'm doing. Technically, this would be 0 plus 43 like this. And then 0 plus 43. That's just 43. So I've got x's only on one side. But now I want numbers on the other side. I want x's and numbers across from each other. So I can eliminate this number that's still on the x side, positive 1, added to a negative 1, you're going to get 0. Again, this would be 0. 0 plus 7x, still 7x, doesn't change anything. So I'm not going to bother writing the 0. I'm going to skip this step just to make things a little faster, maybe a little more smoother. Now I got to do opposite. Opposite of multiplication is division. So now the 7s here are going to cancel. And you're going to get an answer of 6. Now what's happening here, arithmetically, 7 divided into 7 gives you 1. And then 1 times x will give you x. So that's what's going on here. So again, we tend to take a shortcut. We'll just say, well, they're going to cancel, and we just drop them. You get rid of them. But technically, what's going on in the background? Seven goes into 7 one time. And 1 times x is x. But what we'll do is we usually just skip from here. 1. This equals this. Again, you can write division as a fraction. So that's one way of doing this. There's another way. I could have done this. Eight minus 8 is going to be 0. So we'll just be left with 1 equals, and then x minus 8x is negative 7x plus 43. 1 minus 8 is negative 7. And remember, x by itself is equal to 1x. Well, now I got to move numbers. I got to get rid of this 43. Opposite of adding is subtracting. So again, I'll get negative 42 is equal to negative 7x. Now notice, I'm going to undo the multiplication last. We're going to do that last. We'll undo addition, or you might undo subtraction, but those you'll undo first, and then you'll do multiplication last. Or if you have a multiplication in there, you'll do it next. Undo that. So we're going to undo the multiplication. The opposite of multiplying is dividing. And negative 7 goes into negative 7 one time. 1 times x is just x. Negative divided by negative is positive. And sure enough, we get the same answer. So sometimes there's different approaches to these, and you'll still get the same result. There's a couple more of these I want to do before we get into the formulas. Let's see here. All right. So again, we're solving for x. Now, the easiest thing to do here is to distribute. So distribute 3 to x and to minus 2. Then 2 to x and then to 5. And we distribute using multiplication. So that means each object here is going to be multiplied by 3. Each object here will be multiplied by 2. So we'll get 3x minus 6, 2x plus 10. And the cool thing about distribution, it lets us drop those parentheses. Because if you think about PEMDAS says you have to do what's in here first. But if we use distribution, we can get rid of those parentheses. And so we don't have to worry about trying to add an unknown number to 5. X is a number, but we don't know which one it is. And until we do, we can't do this calculation. So if we're supposed to do this first, we're going to hit a rock. But distribution gets rid of these parentheses that put us in that difficult spot. And that's why we want to distribute first. Again, we can gather x's to one side. I'm going to move the 2x by subtracting. So they'll cancel. 3 minus 2 is 1x. But 1x, again, we just call that x. Now, negative 6 plus 7, that's positive 1. So I'm going to redraw this up here. Now you might even just guess an answer at this point. But now I'm going to move this one. Get the numbers all on one side. We get x is equal to 9. So the key with that one, use distribution to get rid of those parentheses and then combine like terms. Let's see, there's one other type of problem they have in here. And then there's a couple special ones we'll look at. Identity and inconsistent. And it's not the last time you're going to use those phrases. They'll come up later in systems of equations. Let's see. So to solve this type of equation, what you want to try to do is come up with a number that 3 will go into and 2 will also go into. So there's some sort of magical number that's divisible by 3 and divisible also by 2. And this number, we can figure it out. It's going to do a lot of good. And I'll show you what we're going to do. Once we come up with this number, we'll multiply each term by that number. And the result will cause these denominators to go away. We want to eliminate the denominators. In fact, I'm going to put all here in capital letters. Because that's pretty hard, working with all these denominators. So what number can we come up with that's divisible by 3, but also divisible by 2? Well, I suggest try to come up with a small number if you can. It might help with some of the calculations. But you don't have to come up with the smallest number. That's usually emphasized in the text. Try to get the smallest common multiple. You don't really have to do this. Anything that will be divisible by 3 and divisible by 2 will work. But there's a small one that comes to mind. It's 6. 6 is divisible by 3, and you get 2. Divisible means there's no remainders. And 6 is also divisible by 2. Gives you 3, funnily enough. So 6 is going to work. This is our mystery number. So what do we do with this? Well, we're going to multiply each term. We have 3 terms here by 6. And remember, when we have a fraction, it means division. It's 6 times 20 minus 6 times x over 3, which is equal to 6 times x over 2. So what this will turn out to be is 120 minus 6x over 3. And we can multiply across. You can think of this 6 as having an invisible 1. Then we multiply these together like we multiply fractions. Top multiplies the top, bottom multiplies the bottom. And every whole number always has that invisible 1. 1 times 3 is 3, 6 times x is 6x. Now, this is going to mean 6 divided by 3. So 6 divided by 3 is just 2. So we have 2x. And then 6 divided by 2 is 3. So you have 3x. And now all the denominators are gone, which is what we wanted. So now I'm going to put the x's on one side. Opposite of negative is positive. And I'm going to take care of this, the subtraction, before I deal with anything involving these multiplications. Now I'm going to undo the multiplication. Opposite of multiplication is division. And let's see, 120 divided by 5, 24. And that's going to be our answer. Let me do one more. Oh, here's a good one. We want to find something we can multiply each term by that will cancel those denominators, eliminate them. So we want some mystery number that's divisible by 5, divisible by 2, and divisible by 3. Now, a number that will always work, you can take 5 times 2 times 3. If you multiply these denominators together, you'll get a number that works. So that's one way you can do that. Let's see, is there any other way? I don't think there is. So we can use a number, 2 times 3 times 5. 30. And you can think of this as like just looking at the prime numbers. Prime, prime, and prime. So any number that's divisible by these, its prime factorization has to contain them. And the smallest such prime factorization would be just 2 and 3 and 5 showing up one time. So that turns out to be 30. Now again, you don't have to use the smallest. We could use 60 if we wanted to, because 60 is also divisible by 5, 2, and 3. I'm just going to use 30. It's smaller. It just makes things easier. So this is the number we're looking for. So I'll multiply each term by it. Now I gotta be careful here. Now, 5 will go to 30 6 times. I can go 30x and 30 divided by 5 is 6. I'm going to show you sort of a shortcut. You can say 5 goes into 30 6 times. So now I've got 6 times x. Or, as we typically write, 6x. Now this one, 2 goes into 30 15 times. Now we got to be a little careful with this one. This 15 is not just multiplying the 1x. It's multiplying the entire top part. So that top part is x minus 3. Finally, 3 goes into 30 10 times. And that 10 is multiplying the entire top part. And that's x plus 2. Now, we've got parentheses. The way we get rid of parentheses is distributing. So we'll distribute 15 to x into 3. 10 will go to x and 2. And again, it's multiplication is what we're using in distribution. Minus 15x. Negative, it's going to take the negative sign with it. Negative and negative is going to be positive 45. When you have negative signs out here like this, they get distributed as well. So now we can combine like terms. Move 15x. Oh, didn't see that 6x there. We'll have to move 6x also. Move the 20 over. And then lastly, again, we're going to undo the multiplication, divide by 19. And 19 is not divisible. I'm sorry, 25 is not divisible by 19. So what we're going to do when we run into that, we're just going to leave it. We'll just leave it as 25 divided by 19 is equal to x. Or we'll leave it for someone who wants to do this long division, wants to take 19 in the 25 and hammer out what that's going to be. We'll just leave it like that. Someone else will come along and want to do it. It also lets us express the answer without having to round off a decimal, which isn't actually our answer. It's a rounded version of it. So the last thing I want to mention, conditional, conditional, inconsistent, and let me see, identity. So conditional. For conditional, there's a finite number of solutions. In all the examples we've done so far, they're conditional. They've had just one solution. So conditional, there's a finite number of solutions. All the equations we just did, we've had one solution. There are other equations where you have two solutions, even 3 or 4. So those are conditional. Identity, let me erase this. And I need some room. I'll give you an example of an identity solution. An identity equation has infinite solutions. There's infinitely many. All the numbers work. So an example, let's take a look here. Let me find a simpler one, just because we're running low on time. I told you we'd finish pretty soon. Let's see here. Find a simple identity equation. All right. So we can gather like terms on this side. We'll get 4x plus 6 is equal to 4x plus 6. 2x and 2x is 4x. Now, once we get this side, it happens to be exactly the same as the other. What this is telling us is that this equation is equal, or this side is equal to itself. Subtract the 6's, you get 4x is 4x. Divide the 4's. And we'll get x is equal to x. So this tells us we have an identity equation. What this means is any number is always equal to itself. -3 is equal to -3. 2 is equal to 2. 0 is equal to 0. Every number is equal to itself. So what numbers are equal to themselves? All of them. They're all equal to themselves. Hence, we have infinite solutions. Last one, and this is it for today. Inconsistent. An inconsistent equation has no solution. So an example of one of those. Again, to get rid of parentheses, we distribute. That will get rid of those troublesome parentheses. 2x plus 2 times 1 is 2. Again, 2 times x, 2 times 1. We're going to take care of the numbers first here. We'll deal with the multiplications with variables last. Oh, that's right, that's not there anymore. And then I could subtract 2x from both sides. Now, in this case, I'm going to have nothing on this side because this will cancel out. So I'm going to put 0 as just sort of like a placeholder or just something that tells me that we really do have 0 on the other side. And then I'm just going to have 1 over here. So everything canceled to 0. But we've got a 1 over here. Now is 0 equal to 1? No way. This isn't true at all. So this tells us we have an equation. When we solve it, we get nonsense. And when we get nonsense, that means we have no solution, or in other words, it's inconsistent. In other words, there's no value of x we can choose that makes this true. 1 is never equal to 0. So no solution. So that's it. So what I'm going to do is, again, I'm going to take a look at what I can figure out with those videos. If you don't mind, would you mind, when you sign out of the meeting today, click that link and see if that takes you to the Teams page instead of the meeting. And if it does, let me know. And then when you're on the Teams page in Microsoft Teams, if you can get there, look for the little link that says Video Lectures, and then click on that. And then when you're in Video Lectures, click on the link to the video and see if it opens up for you. So just to show you what that looks like in here, I'll switch off the recording.